So good morning, everybody. It's good afternoon for myself and my colleague Jorge. I'm bringing to today this webinar on containment strategies from the Austar group. I hope you can understand my English accent. If there's any problems, please ask the Spanish colleagues and they can stop me and ask me any questions along the way. Sorry, I just get my screen back. Okay, my name is Paul Hudson. I'm the director of Austar UK Limited. I'm also the vice president of Austar for Global Operations Excellence and also the technical VP for my business unit. I live in a place called Huddersfield in the UK. I'm a time-served craft engineer with a postgraduate degree in manufacturing excellence. I do have over 40 years experience working within a manufacturing environment. 30 of those years I've been involved with delivering pharmaceutical and aseptic solutions, and I've worked throughout the globe. I've worked throughout the planet. My skill sets lie in operations, technical, site services, and new product development. I have been a manager since the year 2000, and since the year 2008 I've been part of an executive management team. And during my travels with work, I've visited over 60 countries. So the goal of today's presentation, I'd like to discuss containment. I'd like to provide a better understanding for controlling occupational exposure to compounds that could be hazardous to health. Explain containment solutions that are in the marketplace, particularly from Austar, and also touch on testing for compliance once the equipment is installed within your facilities. So first we'll talk about containment and try and understand what containment is. So it's the separation of product and process from people by a barrier. If we look at ISO 14644, it describes that barrier as a separative device. So what is a separative device? I'll take my camera away so we can see that. Separate devices assure protection by utilizing a physical or a dynamic barrier. Now, if we talk about a physical barrier, that is, let's say, glass or perspex between the person and the product. A dynamic barrier can be explained by pressure or moving airflow in a particular direction to take away any hazardous compounds. These are both separative devices. You can use one or both or the other, but they can be placed between the operation and the operator to create containment. So what is containment in a GMP environment? So we're looking at product protection. We're looking at protecting the environment, stopping cross-contamination, and also one of the main factors, operator protection. So we want to protect the operator from the product. So that's protecting people from the product. We also want to protect the product from people. The environment needs protecting as well, because the compounds that we're handling within our facilities could be hazardous to the environment. So we want to protect the environment also. Cross-contamination from people to people, from product to product. We want to protect that also. That's the sort of definitions that we're looking at within a GMP environment. Why would we consider a containment solution? One of the most important things is operator protection. We want everybody to come to work and go home in the same condition as they came to work. We cannot leave protection of the operators to chance. We do have to have a physical solution there. We want to stop any cross contamination or migration of products. To do that, we need to contain at source, protecting the external environment. How do we do that? We need to correctly design filtration systems. So we're not removing the product from source and then placing it out into the atmosphere. We do that by designing filtration systems suitable for the product. We have to conform with regulatory and industrial expectations. So the likes of following standards from EU GMP and ISPE guidelines, and also regulatory such as the FDA, WHO, etc., etc. And also product protection. I heard this the other day. Viable particles are generally human generated. So we must protect the products from the particles that come from humans during the operations. What is a containment strategy and risk assessments? So, containment solutions, there are many of them. They're all designed, the applications are mainly dependent on product and process. These are some of the main categories. LEVs, downflow booths, RABs and filling lines. So RABs are restricted access barrier systems. We have containment isolators. We also have aseptic isolators. All of these solutions can be specifically engineered to meet exacting user requirement specifications. So these are not standard products. All of these products can be engineered specifically to suit the product and the process. We have to do risk assessments before we move forward into designing a containment solution. And why would we do that? Because the products that we're working with usually are quite dangerous. So we need to look after the operator's health. So a health-based risk assessment for operators and also for product. Don't forget, we've got to protect the product. So a health-based risk assessment, especially required for potent compounds that have a potentially serious toxicity profile. And appropriate health-based risk assessments can also determine standard operating procedures. So you can already design your SOPs before you actually go into production. So there's no risks involved when you are handling these hazardous powders. So when you carry out a risk assessment, it's good practice to involve managers and employees, such as operators, as much as you possibly can. So you get a good cross-reference of employees that can all contribute towards determining the solution. If there's not any expertise in-house, there is a lot of external organizations that will help out. Austar can help you. Austar will help you. Main thing is involve as many employees as possible. And if you do that, you'll encourage them to share the ownership of the finished assessments and then the finished solutions. So how do you define the correct solution for your product and your process? Well, to help you, we've put together a guideline, and there's many of these if you do an internet search from many companies. I was quite lucky, but way back many years ago, to be part of the first original one that was ever generated by a company called Extract Technology. And that has been continued over the years to put together a matrix to help end users have guidelines so they can choose whichever solution is suitable for their product and their process. So this is what the strategy looks like. It's a simple matrix which uses OEB classification. It also uses the OEL levels, which you can usually find on the data sheets of any products. It aligns those exposure levels with the type of containment solution. So all the ones that on the previous slide are in there. And also it talks about the toxicity levels from non-toxic through right to highly toxic. These, like anything else, are only guidelines for selecting the solution. There is crossovers, upgrade or downgrade does occur. Therefore, considerations were made dependent on the outcome of the risk assessment. That's why the risk assessment is important. Each individual process should be subject to an employee's or an assigned third party safety risk assessment, taking into consideration, consideration, but not limited to the following: the quantity of product that's being handled, how long will that product be handled for, the OELs of that product, any ancillary equipment that's been used in the process. The ancillary equipment could disturb the airflows, could affect the pressures. What standard operating procedures are in place? And a very, very important one is the operator trained to work on that equipment. And I say that because if you train only one operator and that operator leaves the business, you then don't have anybody who has been trained correctly to use that equipment. You may then put somebody in a position where they're at risk if they don't know how to operate the equipment correctly. And some of these bandings may change because some of the end users that we work with do have different interpretations of these. So I must go back and I must stress that these are guidelines and a good starting point to defining your containment solution. So we will start now with LEVs and downflow booths. So LEVs are local exhaust ventilation. If we go back to our containment strategy and the guidelines within there, protect operators from products with OELs between 100 and 1,000 micrograms. This is a typical LEV solution. LEV solutions can be very, very effective at removing dust and fumes at the source of generation. So they take the particulate away before it goes into the operator's breathing zone or even into the surrounding area. So we're taking away the risk of cross-contamination also. An LEV can be designed in many configurations, including booths, hoods, or cabinets. We have a schematic here with one example of a hood and a booth there, which is connected into the same exhaust system. Inside that exhaust system, there will be filtration, a fan pulling the air through the system and exhausting it away to atmosphere. We go back to protecting the environment because we are dumping clean air out of the system because we have put a correct filtration system in place to remove all those particles. So at this point here, operator and cross-contamination is handled with. At this point here, the environment is protected. And how does that work? When we are dispensing or tipping, the airflow is such that any particulate that becomes airborne during that process will be exhausted away into the system, taken away through the filtration, and as I say, exhausted. So it takes everything away at source, transported away to the filtration system, remove it from the filtration system, and then take the exhaust air out of the building. So we now talk about downflow booths. So these for higher containment levels.
Paul, excuse me, Paul.
Yep.
We've got a question here.
Okay, good.
Asking regarding what norm, norm you use to classify the OEB.
The products usually come with an OEB attached to them, so the analysis have already been done on the product. If it hasn't, you would engage an expert in a third party to be able to do that evaluation for you. So ideally, the product, if it's been in production for quite a while, will come with an OEB level already. If we go back to the matrix, you'll see there's an alignment between the OELL and OEB as well. So that should come from either the manufacturer or you should use a third party to analyze that product. But it is a good question. I hope that answer is sufficient.
Well,
okay, shall I continue?
Yep. Yes, please.
Okay, so downflow booths. We can protect down to 10 micrograms. So we put these in the band between 10 and 100. So a downflow booth, it actually recirculates air. So the schematic here shows us we have in the middle of the system a fan system, which moves air around the system. It recirculates. From that fan delivers into a ceiling plenum, and then through distribution screens, usually HEPA filters, it pushes the air down at a very, very steady volumetric velocity. And if there's any dispensing or powder generation here at the source, it removes it from the airstream purely by the dynamics of the air, and then it takes it away into a filtration system. So fine dust filtration system, HEPA filtration system, so that by the time it gets to the fan, all the dust has been removed, and then we can deliver it. We can almost create an aseptic environment inside there by delivering through terminal HEPA filters. To make it work, we push a little bit of air out of the system, so we get a nice refresh rate inside there, which naturally is drawn back in again. So we also get some air changes through this system. Very, very simple systems, very, very common in place, but very effective at protecting operators. They create a clean environment, and also it allows the operators to work in there without the need for PPE, because it keeps the dust away from his breathing zone. In some special cases, we can control between 1 and 10 micrograms by actually placing a physical barrier in there. So we're using dynamic barriers here, so it's airflow, but if we place a physical barrier inside there between the operator and the product, we can get down to very, very low levels. But this has got to be with stringent SOPs and also very, very small scale sampling, weighing, or dispensing. So downflow booths come in various sizes, right from 1.5 millimeters wide, 1.5 meters wide, that's the distance from there to there, up to 5 meters and beyond. So they can be designed specifically to have your process fully contained inside this area, which allows operator protection, and it also stops cross-contamination, because any of the dust source which is generated within this area here is exhausted into the filtration system and removed from the airstream there and delivered back as clean air. So now we will talk about containment and aseptic isolators. So many isolator applications. They come in all various forms, shapes and sizes. Again, as I said before, specifically designed to the end user's product and process. So right at the very bottom end, the cheaper solutions, the single-use solution, are flexible film isolators. Generally containment, a cheap solution, single-use options as well. We have containment isolators. These are rigid wall from stainless steel, and also aseptic isolators. So we can contain and protect the operator from the product, but we can also protect the product from the operator. And also there's very large filling line isolators, for example, used in finish filling. So we'll start right at the very beginning. We would say on our containment strategy that flexible film isolators are suitable for products with OELs between 10 down to 1 microgram. Again, they can be designed to suit any process. As you see here, there are 6 examples. This is endless what the designs can be. And they are relatively cheap to purchase. They're very effective, and they can be single use. So general specifications for Austar isolators. So both aseptic and containment isolators are made to the same specifications. So all product contact parts are 316L stainless steel. The non-product contact parts are 304, and they're surface finished to a very smooth finish inside, and externally also a good quality finish. Generally have toughened glass vision panels, HEPA filtration with onboard fan and filtration systems. We have controlled pressure cascades. We go back there to dynamic barriers. That's a dynamic barrier there. Inflatable door seals, so we've no leakage out of the system, and also to protect service engineers, we can put on board bag in, bag out filtration. So when it's time to change the filters, any dangerous product that's on those filters, we can also protect the technicians that change the filters. LED lighting, energy efficient fans, and also filters, energy efficient filters on the markets now. We also have alarm packages to show whenever there's any operations out of design parameters. We make the effort to ergonomically design because working through glove ports is not the easiest thing to do. It's quite restrictive, so we have to take the operators into consideration and look at the ergonomics. Also, we want to make sure that the isolators don't leak, so there's an automated leak testing facility on board. We also need to see that the gloves don't leak because you don't want your operator to be actually physically touching the product through tiny pinholes, so we perform a glove leak test on the gloves. And we design our isolators to be technician friendly for qualification, for validation, also planned preventative maintenance. There's simple things like calibrating pressure transmitters. We try and ensure it's easy for everybody to use our isolators. And obviously we have to comply with CGMP, FDA and ISO and other standards. And there's a lot of available options, many options for many different processes. So if we talk about containment isolators, now this is where we get down below 1 microgram. So we've come from the barrier containment within a downflow booth for small scale sampling. We can go to large scale sampling, powder handling, sorry, offer protection down to less than 1 microgram. We can design, and we have designed, down to 10 nanograms over the task. That's very tiny levels. These include designs for sampling, dispensing, subdivision, and also an infinite integration of process devices can be accommodated for. Them are a few of many. Features generally, turbulent airflow, so it's one through airflow. Negative pressure cascade, so the dynamic barrier there is negative, so anything that's inside there is kept inside there. We have our physical barrier, which is the glass windows, and also the dynamic barrier, which is the negative pressure inside there. By having that design, we can guarantee the levels of containment. So if we say it is going to contain down to 10 nanograms, we would design it so it will do that, and also we've got the opportunity to be able to do the validation, which I will talk about later in the presentation. Aseptic isolators, again, rigid wall, but these are designed for aseptic process applications. Inside the isolator, providing a localized grade A environment. The applications can include, but are not limited to, cell and gene therapy, sterility testing, and aseptic processes of any type. Features and options. Obviously, we're always compliant, but you can have aseptic isolators with turbulent or unidirectional airflow, usually positive pressure. We can integrate process equipment. One good example of that is filling line isolators are integrating a filling line. We like to have DOP scanning probes in there to ensure that we've got full face filter leak protection. Inside there, an aseptic solution, we have to know that there is no microbes inside there or any non-viable particles inside there. Paperless data recording, automatic pressure decay testing, and comprehensive validation package are all part of the entire package. If we have VHP on board for biodecontamination, we have to ensure that we have no leaks, so we would put a room monitor on board the isolator. We would also indicate the levels of H2O2 VHP inside the isolator. We offer gas cycle development, so specific to any client's product, process and his load, we will do that gas cycle development alongside of our end user, and also at the same time be training him on how to do gas cycle development. we would offer custom racking, and obviously 6-log reduction testing is part of the gas cycle validation. So next subject would be restricted access barrier systems. Now, there are quite a lot of different variations, but they all create a grade A aseptic environment inside the containment enclosure. Barriers here and here. Now you will see the different types. There is passive and active, and there's also open and closed. The primary difference between RABs and isolators are relating to two things: air overspill and differential pressure, and disinfection and decontamination. Put a bit more clarity to that. Air overspill allows air to spill out of the enclosure. Schematic is showing there. Okay, pressure differential, it could be positive or negative to the surrounding area. We can create that only in an isolator, not in a RABS unit. Disinfection is by spray and wipe. Decontamination is by vaporized hydrogen peroxide and a validatable solution. So there's many different variants on RAB systems, but also they are a different product to isolators. Filling line isolators. Now, if it's for a toxic product, we can guarantee below, as with any containment ISO, less than 1 microgram protection. Filling line isolators are still designed to the same exacting specifications. We can design them with wash in place, clean in place. They all create a grade A environment inside there. We can put on board fully integrated VHP biodecontamination cycles. We can have them positive or negative pressure. It's dependent on the end user and the risk assessment. And that's what a filling line ISO looks like. They are big isolators sat on top of large filling lines. Okay, so now we'll talk, another part of containment are transfer solutions. Transfer solutions designed for product and or waste transfer. So the types we have rapid transfer ports, split butterfly valves, some manual, some are automated. And also, as we talked earlier on, bag in, bag out filters. It stops technicians being contaminated with toxic products. So a quick description of a rapid transfer port, and the next slide does actually show that. It's basically a door within an isolator. When that door's closed, the docking system cannot be used. This is the alpha of the port. This is the beta of the port. Those two lock together. That door can only be opened when that part is in there. So we have product inside here. This door can be opened and transferred into the isolator, or vice versa. Waste can be transferred out of the isolator into this bin and then taken away. So the schematics there on how it works: we bring the port in, we dock it by twisting it. Once it's twisted, the port can be opened. You cannot open the doors without the two components locked together. Split butterfly valves, it's a good way of transferring product from one container or an isolator into another vessel, which could be a bin outside of the isolator. So the split butterfly valve works by having two halves, which can only be opened and closed like the RTP when they are docked together. And it's a valve that cannot be defeated until the two parts are together. So again, it's alpha and beta technology. Again, the isolator can only be as good as the transfer solution. So again, when we buy these, we have to ensure that they're from a reputable supplier who has done their own containment testing, and they guarantee that their split butterfly valves match the OEL of the product. Again, an important part of the risk assessment. Bag in, bag out filters is a system that protects maintenance staff when they want to change out the filters. I won't talk the whole way through it, but basically we can transfer a contaminated filter out of a filtration system, lock it totally away in a plastic bag and send it away for disposal. We can never break this containment line here. We can place a new filter into the system. We can then take away the waste, and then we can go back into production. So that filter that has any that could have contamination on it can never be exposed to the maintenance guys, or in fact the people who are responsible for disposal, for incineration, etc. So, and also we must remember that when it goes outside of the manufacturing facility, it's protected and not contaminating the environment. So now we move on to testing for compliance. So when we have installed our solution, we need to ensure that that solution is working within the design parameters, or else it will not provide the guaranteed level of protection for product or for operators. So many different testing methods. So on an isolator, we will be checking the pressure differential because that's important. That's the dynamic barrier. We would make sure that there is no leakage from the isolator. We'd make sure that the automated leak test is working. Test the gloves, test the glove breach. If you lose a glove out of an isolator, that creates a big hole inside the isolator, which could allow product to come into contact with the operator, or the operator to become in contact with the product. So a glove breach ensures that that doesn't happen in the case of an emergency. The filters have to be tested. If they're not tested, they may have leaks inside them and then not provide the containment. Obviously, we've designed the product to have a dynamic barrier by using airflow patterns, so we have to visualize those patterns using a smoke pencil. If we've got a temperature and humidity sensitive product, we will test the controls of those, noise and light levels for comfort. If it's a containment isolator, we can offer real dust and air validation to ensure that we've designed the equipment correctly and there is no leakage of product out there. There's also a higher level of testing, which is filter membrane capture, again for OEL validation. And then there's a top level SME-PAC testing. On aseptic isolators, we would be testing for non-viable particles, we were testing for microbial particles, and also performing 6-log reduction. VHP is to remove all microbial growth inside there. If there's any particles in there that are viable organisms on them, 6-log reduction confirms that and validates that. SME-PAC testing is a top level testing. The acronym is Standardized Measurement of Equipment Particulate Airborne Concentration. It's derived from a ISPE board for good practice, and this test came out around about 2002, and it's been maintained ever since then. It measures airborne dust. It measures surface contamination. And there's a dedicated validation report issued after the validation to ensure that that equipment is working within the design parameters that it was originally designed to. Glove leak test, very important. State-of-the-art glove port testers, very GMP compliant, no airlines and no wires connected to them. They can be totally wire free to carry out the test by inflating the glove and testing for leakage over time. So we have two types. We have a simplex for single port testing, and also there's a multiple port test system which can send Wi-Fi signals away to a laptop computer to transfer all the test data and also store it for batch record, and then you can have printouts to be compliant. Continuous monitoring inside an isolator has to be part of the design consideration. So we need to monitor for non-viable particles. While we're processing, we need to ensure throughout the process there has been no non-viable particles in there that could have got into the product. We can only do that by continuous monitoring. And it's also the same for viable particles. By using this equipment that is integrated into the isolator, will give us confidence that our batches have been processed without any viable particles in there or without any non-viable particles also.
Paul, Paul, we have a
Yes.
question. We have a question here. The question is SME-PEC test mandatory or should be done at PQ?
It is not mandatory, no. It is definitely part of the risk assessment. Should the end user want to 100% validate, and it's usually a third-party validation team that would carry out that test, so they are confident in that solution, they are confident in the OEM solution, it is the company's choice. It is not mandatory. It is within the guidelines, the ISPE guidelines, and again, the guidelines do not give any clear definition of what you should not do. They do offer guidelines. It is a very expensive test at the end of the day. There are less expensive ways of proving it, but for 100% guarantee of the equipment and 100% guarantee that the SOPs are correct, it is recommended by the ISPE, yes. Okay. Should I continue?
Continue, please. Thank you.
Yes, please.
Okay. So gas cycle development is for aseptic isolators with vaporized hydrogen peroxide generators on board. Now, this is done using biological indicators. This is a biological indicator, this little simple stainless steel disc. On that disc, there's a known quantity of bacterial spores. After exposure to VAP, BIs are then incubated in a culture media for 7 days. If the result after 7 days is this, the gas cycle has not managed to kill all of those bacteria. If it is clear, the cycle is good, so it has managed to kill all the bacteria in there. So this is the part of the validation to ensure that there is full 6-log reduction with inside an aseptic isolator with bio-decontamination on board. A quicker way of knowing that we are getting the gas into the system and it's circulating around the system are chemical indicators. These are usually used pre-validation. A chemical indicator is probably 1/10 of the price of a biological indicator. It gives you an instant readout, whereas you have to wait 7 days with biological indicators, but they help with the pre-validation cycle. Something that's just come onto the market are called EIs, or enzyme indicators. This new technology actually provides instant results. It's not accepted as a validatable technique at the moment, but it gives the same results as the biological indicators do, but it's instant rather than 7 days. So the benefits of EI indicators is that from perspective of an OEM that designs isolators, we can do the gas cycle development more efficiently using EI indicators before BIs, and only use BIs at the validation stage, so we can reduce the price to the end user. So what is gas cycle development? We want to introduce VHP into an isolator. So we have to create the correct conditions for VHP to work inside there. So we have to create the correct temperature and humidity inside there. So this is explained in the cycle. So first part of the cycle is to create those conditions. That's conditioning. When we achieve those conditions, we move on then to gassing. So we introduce a vaporized hydrogen peroxide into the chamber. So we touch every single surface in there. So we'll be killing any microorganism by exposing them to vaporized hydrogen peroxide. In some cases, we'd instigate part of the cycle, a dwell phase. So we hold the gas inside there. So it stays touching the surface. It continues with the kill cycle. At the end of that time validated cycle, we need to remove all the VHP from the system because it's harmful to product. It's definitely harmful to humans. So we need to take it away and also clear it clear it of all VHP before it goes out to the atmosphere. And once we've achieved that, once we've completed the aeration cycle, we can then move forward into production. So we'd go into a sterile operating mode. So if there was any bacteria inside here at this stage, by going through this cycle, it will remove all of the bacteria from inside that isolator. So you can now do your aseptic processing without any risk to the product. So, in summary, the OEL of a product does not define the containment strategy. It also depends on the process. So we've got product and process. We use a risk assessment to define the strategy. What is the strategy? That is the containment solution. We utilize wherever we need expertise. Now, whether it's tapping into the OEM like ourselves or whether it's using a third party, if you're not sure, utilize the expertise. Define a user's requirement specification by utilizing this expertise. By that, you are being GMP compliant. If you have a user requirement specification, you issue it to an OEM, that OEM has to define its solution according to that URS. That URS can then be used right at the very end where we are validating, and we can confirm those design criterias at the DQ, at the PQ, at the OQ. So where we started right at the very, very beginning, we are ensuring that's what we get right at the very end of the project. With having that, we can select the solution, and we must have correct validation at the end of the project. So that, I believe, is my presentation. Thank you very much, and I'd welcome any questions now, please.
Paul, we have two questions here.
Okay.
First one, what is the advantage of soft isolators? When do you use them?
Okay, the advantage of soft isolators predominantly is cost. So when would we use them? Two applications really. Single use. So let's say we are doing clinical trials would be a good example, where we are not 100% sure of the product, the toxicity of the product. So we will do it do the clinical trials under controlled conditions and then throw away the equipment after it's been used once. I've seen it several times where we have provided a flexible film isolator. Inside there may be some weighing scales and other equipment, and they've done one product run, wrapped all the plastic bag up, including the scales and all the ancillary equipment, and thrown it into an incinerator. The second part is it's a cheaper solution. It's less expensive. So some applications, dependent on the product, dependent on the process, renew their flexible film isolators. So they will use it maybe for 6 months, 1 year. When it becomes worn, when the zips start coming worn, or the opaqueness comes in on the plastic, they can just order a new enclosure and place it onto the framework and continue that way. So generally it's used for clinical trials, front-end single use, or for a more cost-effective solution where maybe the budget does not allow, or that it's not necessary to go to the extent of a stainless steel rigid isolator.
Okay, second question. If my product is both toxic and sterile, should I use positive or negative pressure isolator?
My first answer to that would be negative. because we want to contain the toxic product within inside there. And this is the application that I would generally advocate. Containment is containment because that's what we're trying to do. But even though it's still a negative isolator, we can still create the sterile environment inside there. We can, if we need VHP decontamination, obviously that's an option, but also with the monitoring systems that we can place on board, monitoring for viable and non-viable particulate will ensure that the processing is done in the correct manner with no cross-contamination or contamination to the product. But the decision process should be made through the risk assessment. But generally my starting point would be to recommend negative pressure. In my experience, when we've used extremely toxic products and supplied containment solutions, one particular client that I can think of in the past, through his, it was BSL that we were looking at the time, and we actually had a negative pressure isolator at negative 200 pascals. That had an onboard gas generator on as well. So that was an aseptic solution with a toxic product. We can offer advice, all the advice, but we would definitely encourage our client to work with us and maybe a third party to carry out that risk assessment to ensure that we're all in agreement through dialogue that the solution is correct. But just to summarize my answer there, I would recommend negative pressure when a toxic product is in place.
Okay, ¿alguien más tiene una pregunta para hacer? ¿Hay algún tema que no se tocó que quieren mencionar en este instante? Okay, Paul, thank you very much.
Okay.
Hold on, we've just got another question coming in. Hold on a second.
Good.
María, te habilitamos el micrófono para que hagas tu pregunta. Paul, the question is it possible to have a negative pressure flexible isolator?
Yes, generally they are negative pressure. They're generally applied for containment solutions, because we cannot guarantee that they're totally 100% leak proof because the zips on there. So negative pressure is generally the rule of thumb there, or generally the selected option, because they are containment solutions. Wouldn't particularly recommend that we use them positive. But for a negative solution, they are a great cost-effective solution.
Okay, we have one more question here regarding validation of soft isolators or qualification.
Yeah.
And what do you qualify? The negative pressure?
We qualify definitely the dynamic barrier, which is negative pressure. And we can qualify containment as well for OE levels. We're comfortable with that. The ergonomics, obviously, the standard things like noise levels, light levels, never a problem because it's see-through, and it's dependent on how far we've gone with a flexible film. If it's just straightforward one chamber plastic bag, there's not a great deal to validate. We place on, obviously we have HEPA filters on there, so we would have to do the HEPA filter integrity test, because there would be an inlet filter and also an exhaust filter which comes out of the fan unit. So we would have to check at the outlet or if it's going into ductwork. So definitely the integrity of the filters. there wouldn't be a great deal of difference between validation of a flexible film isolator and a rigid wall on the basic design parameters. You know, we'd have airflow change rates in there, fitment of filters, that glove breach tests, all the same design criteria will be in a flexible film isolator. The cost savings are in the manufacturing costs and the material costs.
Okay, and a final question is, which is the concentration of H2O2 used in the cleaning process?
35%.
Okay, that's...
So it's a 35% hydrogen peroxide mix. That's used for, as far as I'm aware, all VHP generator providers. Particularly at Austar, we use Steris, which is probably one of the two top global providers. On our equipment, we fully integrate the Steris unit. So the the H2O2 bottles are fully sealed with RFID chips on board with them, and a very effective system which have years and years and years of validation behind them. But the answer is that the hydrogen peroxide comes at 35%. The levels inside the isolator when generated, the ppm levels get up to over 500 parts per million. So it is a very aggressive attack on the microbial growth, if there is, inside the isolator. And when we end the gas cycle, right at the very end of the gas cycle, we can't allow production until we're down below 1 part per million within the isolator. So fully valid, as I say, that's why I showed the cycle on the schematics. That is a fully validatable package that we would supply with our isolators.
Okay, Paul, we've got another question just came in.
Good, keep them coming.
Is it possible to use a cabinet class 2 if you are working on an analytical laboratory handling less than 10 grams in operation, which is not generous dust for substance OEBs 5?
As an isolator manufacturer, I would say no, for obvious reasons. Not being a cabinet expert, I would not particularly like to answer that one, if that's okay. I think that's entirely down to the end user. Cabinets are designed for containment, yes. Not having worked with them too much in my working career, it would be incorrect of me to say yes or no to that. I would say, please buy an isolator.
Okay, Paul, thank you for your honest answer. And okay, just a word in Spanish. Estamos abiertos, tanto Jorge Nuero en España como nosotros acá desde Argentina, para cualquier aclaración en español o para cualquier contacto futuro, si nos quieren mandar un mail. Jorge, ¿vos querés agregar algo?
No, correcto. Gracias a Paul por la presentación. Y como Marcos comentaba, cualquier duda o si hay interés en esta presentación, la podemos traducir al castellano y la haría yo en unas semanas o si tenemos interés por parte de una audiencia interesada en el asunto. Incluso podemos tener a Paul como apoyo si alguna de las preguntas es muy complicada o él tiene más experiencia que yo en este tema y nos puede servir de backup y de apoyo. Muchas gracias a todos por asistir a este webinar y estamos ahora mismo dispuestos y preparados si tenéis alguna pregunta y alguien quiere lanzarla en castellano en vez de en inglés por cualquier motivo.
Okay, Paul, thank you so much. Basically, what Jorge and I have offered is our Spanish support and to have a contact in Spanish with anybody and refer to you in case there's something which exceeds our knowledge.
Absolutely.
Thank you for your effort and thank you for your help today.
So yeah, thank you for your help to you guys over there. I thank you for everybody to listening to my presentation. I hope that you found it interesting. If you didn't, please give that feedback. Feedback is important to us. So again, thank you everybody, and I hope everybody stays safe and we all come out of this situation in the very, very near future. So thank you and goodbye.
Okay, thank you, Paul. Thank you, Jorge.
Gracias, gracias, thank you.